Hey folks, Mr. Bauer here. So sometimes in AP Physics, you're going to have to work with potential energy versus position graphs. So it's a good idea to know where they come from, to have some idea how you create them. So let's look at an example of something that has potential energy. Oh, let's get rid of that off my screen. There we go. So let's take a look at something that has potential energy, namely an object like just a basic box or a block that is attached to a spring. So let's say here's our spring and it's in a very relaxed position. In fact, this is the spot that we would call x equals 0. It's the equilibrium position of the spring. It's where it's not stretched or compressed. So down here, I'm going to draw some axes for a graph. And the vertical axis is the potential energy that the object attached to the spring has. And the horizontal axis is the position of that object. And so what we want to think about is, if this is the relaxed position of the object, let's think about stretching this spring. So we're really going to stretch it out until maybe the object is over here. Or, alternatively, we could think about compressing the object. So moving it in this direction so that the spring is really, really highly compressed. So what I want you to think about is what would the potential energy of the object look like when it's at this location, which corresponds to this position on our graph down here. And what would the potential energy of the object look like when it's at equilibrium, at x equals 0 down here? What would the potential energy of the object look like when it's stretched out and when it's over here? So actually take a few moments, maybe pause the video and see if you can make a sketch of what you think this potential energy versus position graph will look like. And then you can see whether you're right or not. Okay, well, hopefully you had some time to do that. So, the formula for the potential energy that an object on a spring has is 1/2 kx squared. So when an object's at equilibrium where x equals 0, it doesn't have any potential energy. So we could put a dot right here. And then obviously as x gets bigger, so as we stretch the object in this direction, x gets bigger, the potential energy gets bigger. So we're definitely going to want to increase the amount of potential energy. But it's not going to be a straight line because from this equation you can see that potential energy is related to position squared. So it's actually going to be the type of graph we see when one thing is related to another thing squared. It's sort of a parabolic shape, a curve. So it's going to look something like that. And all this is saying is that as this object gets stretched out to a further and further position, its potential energy is going to increase. And that's because the spring is more and more stretched. On the other side, it really looks identical. As you compress it, the potential energy increases until maybe that's what its potential energy is when it's fully compressed. And as you do that, it's not a straight line, it's a curve. And that's because of this equation right there. So hopefully that gives you some idea of how a potential energy versus position graph is created for an object on a spring. Now there are a lot of other types of objects that might have potential energy, not necessarily attached to a spring. So you can have lots of different looking graphs, but this is what one looks like for an object on a spring. So now if you want to go ahead to the next video of interpreting a potential energy graph, hopefully you'll understand that better.